More students coming. Let's do how to put that. More students coming and I'm recording right now, and by the way, I uploaded the recordings from the previous two classes, right? And let me start sharing the screen here. Share. Right in here. Let's see. So first meeting was just introductions. There was no recording. So I didn't upload anything for this very first meeting. The second meeting on the 28th of August, we looked into the Excel graphs, units, dimensional analysis, and there is a link for a recording. Let's take a look at the right here. Okay, let's not forget those, those recordings there. Here you go. Remember, right? Here's the canvas. Syllabus, the Wiley Plus access, the instructions how to access, right? Here are the notes for the fall 2023, and this is the notes for the fall 2024. There's not much, there will not much be, there won't be much difference between those two notes, but there's always something that I change a little bit, right? So lecture notes for this year, lecture notes for last fall meeting, last fall course. Here are the links for the videos for 2023, right? And you're going to see links for every class meeting that I had that year, okay? How many? 1, 2, 3, that must be like something like 30 meetings. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 20, 21, 22 should be like 12 recordings per page, right? 22, let's see, yeah. Okay, it's 24, 25. Yeah, 25. 25 recordings for last year. But and this year, let's take a look at this year. Like I said, there are only 2 recordings so far. Like I said, those recordings, they are not much different from each other compared to last year. But there is always something that I do slightly different, right? And 28th of August, our second meeting. Going back here to my, here you go. 28th of August, that's the 28th of August. Then we had the Labor Day, no meeting. And then we have our third meeting and our second recording, confidence level for the lab. Today we are writing here and we just started. Let me just add this thing here. It's not, we also start looking at 1D motion, right? And 1D motion, just a little bit on that. Yeah, confidence level and 1D motion. One-dimensional motion. Now let's save this one here. Okay. So far we have 19 students. And that's the syllabus today. We will continue with 1D motion. And hopefully, and we'll be able to have our first lab the day after tomorrow. Significant figures, CL, and so on, right? And significant figures of measurements. That's my notes. Okay, Wednesday. And insert. Page break today is 09/09/24, Monday. More students coming. I'm going to need my illustrations as well. Yep, that's where you are here. And we are talking, last time we were talking about the instantaneous velocity. Okay, and what I did here, I defined the instantaneous velocity in terms of a limit, a mathematical limit. And then I gave you an example what this mathematical limit means for certain functions. For instance, for this one right in here, right? At x equal to 0, you have 0 divided by 0. It's not necessarily an undefined quantity. In reality, when you approach it from the right for x, for x values very close, just above the limiting value 0, this limit ends up being equal to 1. And I proved that to you in Excel. The same thing applies. The same thing applies to other types of functions, okay? Like a tangent of x divided by x. Tangent of x divided by x also should be a 0 divided by 0, but it ends up being 1 as well. So there is, in many cases, not always, right? But in many cases, when you are dividing 0 by 0, you do have a limiting value for this division. Okay, and that's what's the idea of instantaneous velocity is all about, comes from. Okay, so going back to instantaneous velocity, here you go. Definitions, right? Primary, secondary, tertiary, okay, quaternary, and so on, right? Quaternary, and so on. instantaneous velocity, okay? Mathematically speaking, right? Mathematically speaking, the instantaneous velocity is given by that relation that I wrote down here, which always ends up being a finite number. In practice, we cannot make delta t or delta x, delta t and delta x equal to 0. When I mean in practice, I mean in the real world, right? In the real world, we cannot make delta t and delta x equal to 0. However, let's see here. I'll copy this one and put it here. Delta t and delta x equal to 0. Instead, we make delta t small enough compared to something else. Okay? We make delta t and delta x small enough compared to something else. Okay? Like in the case of your speedometer. Okay? How does the speedometer works? How does it work? Okay? How the speedometer in your car, like the speedometer, like in the case of the speedometer in your car. How does it work? Okay? Cars are built, right, to travel long distances, let's say kilometers at least. So what we do is to get a very small distance. What we do is to time in the speedometer. So in the speedometer, we measure a very small distance given by the turn of the wheel of the car, right? So if you are traveling 10 kilometers, right? And your car wheel, given by the circumference, okay, let's put here, not the turn, but the circumference of the wheel of the car. So if you're traveling 10 kilometers, a circumference, a distance equivalent to the circumference, of the wheel is going to be very small. That compared to the overall distance. So we time how long the wheel takes to travel this distance. and divide, okay? Circumference of the wheel, I'm gonna write that down as being C, okay? C. So we time delta x, and even I'm gonna write that down, delta x equal to C. Equal to C. So we time how long the wheel takes to travel this distance, delta t, okay, comma, and determine the so-called instantaneous, I'm going to put here instantaneous velocity, so-called instantaneous velocity. In this specific case, delta x and delta t and delta x delta t and delta x are the measurements of the device, and the instantaneous velocity is the result of your two measurements. Very important difference, okay? Remember these two differences. Measurement and result. These two important differences. Measurement and result, okay? Okay, there is another way of determining the instantaneous velocity. There is another way of determining, I'm going to put it between quotes, not just the instantaneous velocity, but the average velocity as well. This other way, okay? This other way involves plotting the x position along the vertical axis versus the instant of time along the horizontal axis. Okay, we do that in physics a lot, okay? Or x versus t, okay?
Professor, is it okay if you scroll up a little bit? I just want to write the formula down.
Let's see, you mean too small, you said?
Oh, I just want to write down the formula. If you could scroll down a little.
Okay, here you go.
Okay,
That's
thank
the
you.
one. Yeah. So it's this is a straightforward formula, right? Limit. This lim here means limit, right? Limit of delta x over delta t whenever delta t goes to zero and whenever delta x goes to zero. Okay? That's a mathematical way that we encode, right? This definition. Okay, so the above, I'm gonna write that down here. Limit the above formula is said uh, to be the limit of delta x over delta t of delta x over delta t. Okay, as both values goes to zero. Both values go to 0. Okay, so let me take a little break here. Okay, I gotta go downstairs, and while you copy all of that, and I'll be back very soon. Okay, hang in there. Okay, so let's take a look at my graphs here. Right, here you go. This is the one-dimensional x-axis. You saw that before. And now I'm gonna plot, here you go. I'm gonna plot x versus t, right? We start with the t-axis that lies along the horizontal direction, and the x-axis that now lies along the vertical direction, origin, everything. We go ahead, divide the horizontal axis in 1 second, right? And we divide the vertical axis in 1 meter. Each distance here is along the axis is 1 meter of difference, okay? And here you go. We are plotting the position of a particle in terms of this graph. That's a representation that we do. Okay, given a time t equal to 0, the particle is a position 5 meters. And a little bit later is a position 3 meters. A little bit later, I mean 4 seconds, an instant of time, 4 seconds, or 4 seconds later, it's a position 3 meters, okay? Now, and then between 0 and 4 seconds, there is this, there is a bunch of other points that I'm not displaying here, okay? But in real life, that's what it happens, right? As the particle is moving along the x-axis, along the horizontal axis, you must have some other points along between these two other points here. And today, with technology, we can get all sorts of points for the position of a particle. Okay? Now, if you plot a straight line from this point to this point here, and then measure the slope of this straight line, what you end up getting is the average velocity of this particle. Because the slope is going downwards, it means that because this line is going downward, it means that the average velocity is going to be negative. Okay? And here you go. Rise in this case is going to be minus 2 meters, and run is going to be 4 seconds. And then calculating the average velocity, we are going to get minus half meter per second. That's the graphical interpretation of the average velocity. That's the graphical interpretation of the average velocity, the slope of the curve between those 2 points in the graph. Okay, we can go ahead and let's see, maybe I can even add this graph to my notes, right? To make things easier for you. The only problem about adding those graphs to my notes is that the file ends up becoming huge, and becomes very difficult later on to open it again. That's why I don't like to do that, but let's try that. Here you go. I'll copy that and paste here. Okay. Graphical example of the average velocity. Right? Here you go. Okay, and now I'm going to describe it in words, right? Graphical example of the average velocity. Okay. In the case of the average velocity, we may determine the this parameter by connecting the 2 points of the above graph with a straight line. Okay, with a straight line. The average velocity will then be given by the slope of this line. Okay, because the angle of this slope is more than 90 degrees, right? Not more than 90 degrees, it's between, not more than 90 degrees, it's between 90 and 180 degrees, comma, then the slope will be negative. That's an example. Okay. And okay, so here you go. I'm going just to spell out the whole thing, right? Here you go. In words, let's see here. Graphical example of the average velocity. I'll start writing here. In this case, one, we plot 2 points, 0, and here is going to be 5 meters, not 4 centimeters, but 5 meters, right? And here is going to be 4 seconds and 3 meters. 3 meters. Don't forget that here in this case, the x-axis is t, and the y-axis is x. It's 2 points, t and x, right? We plot 2 points, okay? Here should be 0 seconds, 5 meters, 4 seconds on a graph x versus t. Then we connect these 2 points to a straight line. Finally, we measure the slope of this straight line. The slope of this line coincides with the average velocity, right? The average, here I'm just repeating what I wrote down up there, right? Then the slope will be negative. The slope is negative too whenever the points are going, the line is going to go going down, right? If the line starts going up, then becomes the average velocity becomes positive. What about for the instantaneous velocity? What about for the instantaneous velocity? For the instantaneous velocity, okay, you need more than 2 points. But the procedure is similar. You actually need a line. You actually need a line. You actually need a line. And if deeply, okay, but the procedure, let's leave this way, but the procedure is similar. So how does it go? Like that. Initially, you must have a graph of x versus t, a smooth graph. This must be given. Today, like I said before, with technology today, it's possible to obtain a graph with several points along the t-axis. Okay. Suppose you want to know the instantaneous velocity. Let's say at a given instant of time t2. Let's see if I have a graph here. See here. Oh yeah, here you go. Okay, so here you go. Now we have our 2 points, right? And I have this fancy device that can collect the position of this particle at very small intervals of time. It's possible to do that with current technology. We do those things in the lab nowadays. At the time of Galileo Galilei, back in the 1500s, they didn't have this type of thing, but today we do have it. It's amazing how technology has progressed, okay? Here we are assuming that we know the position of a particle as time goes by, for let's say every tenth of a second, for every tenth of a second, right? Or even for every hundredth of a second. It's possible to get something like that. Okay? So that's the first step. Initially, you must have a graph of x versus t, and here we have one, which was collected with our fancy instrumentation. And now suppose that you want to know the instantaneous velocity at time t2. Let's see if I illustrate my t2, okay? I want to know the instantaneous velocity at time t equal to 1 second, for instance, right? That would be my t2. And let's make sure this is exactly at 1 second. Yeah, it is, right? Yeah, it is. Here's my x. Okay? And I'm going to be even more at t2 equal to 1 second. You get 2 points on the graph, one at t2 and the other at any other point along the curve, say t1. Okay. Okay, we refer to the definition of the instantaneous velocity. That's t2, and let's say the other one is this one right here. Okay, it's this one right here. And what we do, okay, let's just start instead of okay, we want to know the instant of time, the velocity, the instantaneous velocity at this point, right? So instead, let's get those 2 points. Since we started with those two initially, let's get those 2 points, okay? And that's what I did in the next one. Here you go. That's the slope that you're already familiar with because we looked into that before, okay? And what we are going to do, we are going to make delta t goes to zero little by little. Right now, delta t is 3 seconds, okay? Right now, delta t is 3 seconds, and we are going to shrink this delta t, and in the process, we're going to shrink delta x as well. Here, delta t equal to 3 seconds, the delta x is going to be 1 meter. And then, here you go, what I did next. I am shrinking this time interval. What was 3 seconds now? It's not going to be 3 seconds anymore. It's going to be almost 2 seconds. What was 1 meter difference now is going to be something around 1 meter, a little bit less than 1 meter, right? Half meter, let's say. And then we take this slope just like we saw before. In this case, now the slope became positive, right? And we are making delta t go to zero. Okay, as delta t goes to zero, we come closer and closer to the actual instantaneous velocity. Here you go. Now it's going to be those 2 points here, which are spaced by less than 1 second. Okay? Eventually, we reach a point in which the delta t is equal to zero. The point where delta t is equal to zero corresponds to a straight line that's tangent to the curve. Let's see. Let's see here. Yeah. Yes, LIM means limit. I'm missing your questions here in the chat, right? Yeah, LIM means limit. Uh-huh. Yep. How did you shrink the 2 points? How did you do that in the calculation? Okay. The way we do it, let me give you an example. So how did you shrink the 2 points, right? How did you do that calculation? And yeah, that's a very good question. That's something that I didn't mention, right? Remember what we actually do. Unfortunately, I do not have. Let's see. Let me do a very real life situation. Okay. Here you go. We are going to study that. Here you go. I'm gonna put like that. T in seconds, right? And X in meter. I'm gonna give you an actual real life table here so you can understand better. Let's see. I'm going to put 0.1. Suppose that I have this data that was collected by my fancy instrumentation, okay? Just like I mentioned, we can collect this type of data with existing instrumentation. Okay, and now I'm going to get something like half 9.8. Okay, I'm going to come up with a very simple example. Okay, like that. So let's say my instrumentation got all this data that you see right here, and that's too much here. 98 is too much. Let me put 0.98. Okay, 0.98. It's better like that. I'm gonna go all the way up to 10 seconds right here. Okay. And now I am going to plot, here you go. This is a real life experiment. It's okay. And now we have my X versus T. That's my X versus T graph. And let me shrink a little bit more. Shrink a little bit more here. I'm going to format my graph. I'm going to add axis titles. That's going to be my T. And that's going to be my primary vertical, X. Okay? Bold face here, bold face here. I don't like to keep graph titles. Okay, so I take out that graph title. So now let's say for this specific graph, I want to, let's see, 1, 2, 4, 5, 7. Okay, I want to, instead of one, let me make this graph very similar to this other one, okay? 0 to 5, 0 to 5, and 0 to 5, okay? So instead of going all the way up to 10, let's 0.05 here. Here you go. Okay, and now we have this graph here. Okay. And well, if you want to know the average, and then I'm going to use this graph here. If you want to know the average velocity between 0 and 5 seconds in this graph, all you have to do is to I'm going to add another figure. I'm going to come up with a different graph here, right? The one that I plotted in Excel. Here you go. Right? And here you go. Now, assume you know the position. Oh, we're going to repeat what we're doing with this graph here. Here you go. Now, assume we know the position of a particle as time goes by. Right? This data can be obtained using some fancy instrumentation we have in the lab. Fancy instrumentation we have in the lab. It's possible. Okay. I need. Here we go. Number, general, number. Those numbers are too small for me. Let's see if I can do better than that. Yeah, there must be a way to do it. Well, I'm not gonna struggle with that, okay? Now we know the position of a particle as time goes by. This data can be obtained using some fancy instrumentation we have in the lab. Okay. Next, want to know the instantaneous velocity of this particle at time. I want to know, instead of 1 second, okay, I'm gonna get here, instead of t equal to 1 second, I'm gonna get it here, t at 3 seconds. I want to know the instantaneous velocity of this particle at time t equal to 3 seconds. Okay? I'm changing here the script a little bit. 3 seconds would be right in here. Okay. And I'm going to make it thicker to make it easier to see this point. Okay. 3 seconds. Font. Okay, I can change it here. 14. Yeah. Font. I'm going to put bold faced as well. Let's put font size 20. Yeah, bold faced. Here you go. Now it's easier to see this data, right? Bold face 20. Here you go. This one is going to be 25. It's going to be bold 25. I can make it nice by, italicizing. Here, do the same thing. Don't forget, when you do your graphs in the lab, you gotta do something like that, similar, right? And I'm going to italicize as well. Here you go. 3 seconds. That's going to be my 3 seconds right here. Okay? I want to know the instantaneous velocity of this particle at time t equal to 3 seconds. Remember, I'm changing the script, right? Here you go. Yeah, here you go. Now it's a nicer graph. We can see those points more easily. Let's see. Yeah, better. Okay, and then what we do first? Okay, we refer to the definition of instantaneous velocity, right? We refer to the definition of instantaneous velocity. And that's the one. Okay. And the first step is to get a delta t. The first step is to get a given delta t. Okay. First, first step is to get 2 arbitrary points. First step is to get 2 arbitrary points in an interval that contains t equal to 3 seconds. Okay? That's the first step. The most obvious 2 arbitrary points would be, here you go, t equal to 0. And I'm going to put it like a black. And t equal to 5, right here. equal to 3 seconds, okay? And we do exactly what we did before. We do exactly what we did before, right? So we go ahead when we calculated the average velocity. We get a line connecting those 2 points. First step to get 2 arbitrary points in an interval that contains, in this case, delta t is equal to 3 seconds. Mhm. Okay. Right in here, symbol. Delta t is equal to 3 seconds. Okay, and calculate the average velocity, calculate the slope. In this case, the slope is going to be 12 divided by 5, which is equal to 12 meters divided by 5. Can you see that? Right? Delta x, delta t, right? And delta x over delta t. Okay? 12 divided by 5 is something like 2.4, right? 2.4 meters per second. The slope. And then what we keep on doing, we keep on shrinking. Then we keep on shrinking. Next, we keep on shrinking this interval. Let's say now instead of between 0 and 5, is now between 1 and 4. Okay? Next, we keep on shrinking this interval. So if delta t was 3 seconds now delta, no, it's not 3 seconds. Let's see. Not 3 seconds, it was 5 seconds. Here you go. If delta 3 was 5 seconds, now delta t is going to be 1 to 3 seconds. Okay? And we redraw the slope and calculate this slope again. Right? The slope becomes 3 meters, becomes, let's see, I'm going to estimate that, okay? I'm going to estimate that. But I can even look at the graph. I can even look here at the graph. Delta t between 1 and 4 seconds, right? I can go, the graph, no, the table. Between 1 and 4 seconds, here you go. 1 and 4 seconds, right? Is 7.84 minus 0.49. 7.84 minus 0.89 meters divided by 3 seconds. And then you do the math, okay? Going back there, let's take a look again. 0.49, let's see, 7.84, 0.49, let's see, 0.49, okay. And then you do the math. We're gonna do that here for you, okay? Calculator. And you keep on doing that several times until your delta t is small enough. Okay, divided by 3. This when I do the math, it is 2.45 now. 2.45 meters per second, okay? But rather than the numbers, the most important thing that you have to keep in mind is not just the numbers, but what happens to the curve as you keep on shrinking this interval. Okay, as you keep on shrinking this interval, you have to notice something interesting here. Okay, this slope that you see right here ends up getting closer and closer to the tangent to this curve. Okay, and as you keep on shrinking this interval, you are going to get exactly a slope that coincides with the tangent to the curve. Okay, so let's write that down here. As you keep on shrinking delta t, comma, the slope gets closer and closer to a line that is tangent to the graph. Okay, that's the process of limiting. That is the process of limiting, of limit. Okay. In this case, when and we can keep on doing that with with this data that you see here. Okay. So I'm gonna do let's take the average velocity, right? Here you go. Average velocity between V average, AVG. First, between 0 and 5. Okay? So here you go. First, between 0 and 5, delta x. Okay, here you go. Delta x here minus delta x minus delta x is going to be 12.25. It's going to coincide, right? 12.25. Divide by this one. You get 2.45. That's my first average velocity. And then we shrink this time interval. It's very important that you do that in Excel as well, so you can get the idea. Okay, and I'm gonna put some more information here. Between 0 and 5, right? 5 seconds. 0 and 5 seconds. Yeah, and then we shrink this interval, right? The next interval that I did. That's the nice thing about having those software Excel between 1 and 4. Okay, between 1 and 4, 1 and 4 seconds. Now we shrunk between 1 and 4 seconds. It's going to be like that. You go 1 and 4 seconds, 7.84 minus 0.49 divided. Well, I already know that's 3 seconds, so you can put that 3 seconds here, right? J82, yeah, point J82, 784. In this case, it coincided with the previous slope. And then we're gonna go the next step. So let's say instead 1 and 4 seconds, now let's get 2 and 4 seconds. We're shrinking it even more. Let's see here. Did I put it? Oh, I put in the wrong place here. This one is supposed to be this one here. Let's see. No, that's all right. Yeah, that's the right one. Now 2 and 4 seconds equal 4 seconds. 4 seconds minus to the position, corresponding position at 2 seconds, right? 4 minus 2 is going to be 2. Okay, here was the same as this other one. Here is different, right? And then we keep on shrinking this interval. 2 and 4 seconds. Now, let's say now is 2.5 minus 3.5. We're getting closer and closer to 3 seconds, right? So here you go. I will copy this one, paste it right in here. The equation is going to be different. It's not going to be J82, right? It's going downstairs. Is going to be just 1 second. 2.5 seconds is going. I don't have exactly 2.5 seconds. 2.5. Oh yeah, 2.5 seconds. I have it right in here. Yeah, it's going to be this one here, right? 2.5 and 3.5. Yeah, 3.5. The X position at 3.5 seconds. And then what do I get? 2.94. And keep on shrinking as much as you can. Okay, next one. So let's see, the smallest interval that I can get here at exactly 3 seconds is going to be 0.05. Okay, 0.05. Going to be this one right in here. So that's the smallest interval that I can get. And I'm going to be equal, open parentheses, the position at 3.05 seconds minus the position at 2.95 seconds. Do you see what I'm doing here? I'm shrinking it, this interval over and over. And then 3.05 minus 2.05. That's going to be 0.01. Okay, and then what I get? I get that's going to be the value that's be the closest to your tangent. And let's see if I can put more decimal places there. Number, let's see. I'm gonna put as many decimal places as I can so I can, yeah, they're almost the same. See that? It's tending towards this value, 2.94. And 2.94 is going to be the value of the slope of the tangent in this specific case, okay? So that's how but most important, what you have to memorize is that as we shrink the interval to 0, delta t equal to 0, this slope gets closer and closer to the tangent of the curve of your graph. If we do that for this graph, it's going to be something like that. And here, for this other graph that's different, it's something similar, right? Here you go. The slope is getting closer and closer, and eventually getting closer and closer to the tangent, and eventually becomes the tangent itself. Okay? So that's the idea of the instantaneous velocity. That's how you find the instantaneous velocity. Here you go. Initially, we must have a smooth curve of x versus t. Suppose you want to know the instantaneous velocity at t2 equal to 3 seconds. Okay? Here you go. You get 2 points on the graph. Instantaneous velocity at t2 equal to, you get 2 points on the graph that contains t2. Okay? 2 points in the graph that contains T2. Here you go. You connect these 2 points, connect these 2 points to a straight line and find the slope. In the next step, you make, you take a smaller interval that contains T2 again. That contains T2 again. okay? And find the slope again. And find the slope again, okay? Eventually, as you shrink, your interval, you will notice that the slope of the curve, the slope of the slope of the line connecting the 2 points gets closer and closer to the slope of the tangent. That's the central idea of, in conclusion, the instantaneous velocity at any point along the x versus t curve is the slope of this tangent. Okay, I'm going to emphasize here. 9:57 right now. Okay, so what I want to do, I want to take attendance. Today is the 9. That's also a holiday. Let's put Labor Day. Audrey Aguilar, are you there? I think that Audrey.
Yes, I am.
Oh, okay. Okay, it's the other Audrey that dropped, right? Yeah, it's the other Audrey that dropped. Thank you. Matthew Aguirre Mata.
I'm here, Professor. Good morning.
Good morning. Thank you. Darius Blending.
I'm here. Good morning.
Good morning. Brianna Carrillo.
I'm here.
Thank you. Jesse Castellano. Okay, Jesse is here. Gabriel Contreras.
I'm here.
Thank you. Liliana Cortez.
I'm here.
Next is Juan Escalera. Okay, thank you, Juan. Molly Fitzgerald.
Here.
Okay, Henry Kim.
Here.
Okay, Ruth Mandujano. I see Ruth here in my roster, but I don't hear from Ruth. Noemi Martinez. Hello, Noemi. Okay, I see Noemi here in my roster. Danae Miller.
Here.
Thank you. Ramon Olivares.
Here, Professor. Good morning.
Thank you, Ramon. Taylor Fawn. Let's see if Taylor is here. Nope. At least I don't see it. Okay, Alexis Quijada. I don't see Alexis. Stephanie Ramos.
I'm here.
Stephanie is here. Okay, thank you. Jeremiah Reyes.
Here.
Thank you. Matthew Ritchie. Are you there, Matthew? Matthew Ritchie. I don't see Matthew here. Yes. Next is Sean Rosario.
Here.
You're there?
Yeah.
Okay, thank you. Next is Ali Standard. I don't see Ali here. Okay. Jason Straight.
Here.
Thank you, Jason. Elena Trujillo. Hello, Elena, are you there? I'm gonna put a star here for Elena. Next is Jason Valadares.
Here.
Okay. Next is Stephen Vadhapali. Noemi. Okay, thank you, Noemi. Noemi M. Okay. I don't see Stephen here. Laurel Williams. Hello, Laurel. Laurel seems to be here, but it's not answering. Nuhamin Wandimu. Thank you. And Aliyah Zavala.
Here.
Okay, was everybody called? Was there anybody whose name was not called?
Oh, hello.
Yeah, what's her name?
Stefan.
Stephen, what,
25.
25? Ah, okay. So which name are you in the roster here, Stephen? What's, oh, yeah, okay, I see it, Stephen Laspali. Okay, good, thank you. And let's give another opportunity for the other. Ruth, are you there, Ruth? Okay, Ruth, and 1, 2, 3, 21. Let's see. Elena Trujillo, are you there? One more option, one more opportunity here. And Larell, 24. Yeah, okay, those numbers match. Let's see. 1, 2, 3, 24. Okay, good. Those numbers match. So let's go for our break. Right in here. Break 10:05 to 10:20 a.m. Okay, and then just to repeat what I said, you might want to do exactly what I did, to practice those ideas of instantaneous velocity. Okay, what I have here is an actual case in which is a special type of motion that we have here that's called uniformly accelerated motion that we are going to study, in which I was able to illustrate the idea of instantaneous velocity, how you can get the instantaneous velocity from a graph of x versus t. Okay, and you Excel is a very powerful tool that allows you to, to illustrate those concepts that we are covering here in a better way. Okay. So you can visualize the concepts in a more straightforward fashion, okay? So let's go for our break, and I see you in 15 minutes. Okay, so someone is asking about the homework, right? Let's take a look at the homework that we have that are Wiley. As far as I remember, the first homework is due in October. Let's take a look there. Wiley plus right here. Yeah, okay, yeah, October 2nd, right? There's no homework due until October 2nd. So I already assigned chapter 1 and 2. Very soon I will assign the other chapters for this course. Okay? Am I sharing the screen, by the way? Yeah, I'm sharing the screen. That's good. Great. Okay. Okay, so in this course, we're going to study different types of motion. We're going to study different types of motion, okay? The simplest of all motion is the one with is the simple of all motions is the one-dimensional motion with constant velocity. That's the simplest of all motion that we're going to see out there. Constant velocity. Simplest of all motions is the one-dimensional motion with constant velocity. And in order of difficulty, okay? In order of difficulty, one-dimensional motion with one-dimensional motion with the object at rest. At rest, okay? So if you plot this type of motion, will be something like that. The position of the object against the instant of time. Note C, the object, and here x naught is the initial position of the object. Here in this case, the object is not going anywhere, okay? The graph of this object is just a straight line in the horizontal direction. In this specific case, the slope of this graph is going to be 0. Special case of velocity equal to 0. I want to write that down here for you. Here we go. Slope is equal, slope of the curve, right? Of the curve is equal to 0. It's equal to 0. By the same token that you can plot the position of the particle versus the instant of time, you can also plot the velocity of this specific particle against the instant of time. And if you do that, you get this type of graph, right? We do have a straight line. The straight line is in the horizontal direction, and it coincides with the t-axis to indicate that the velocity is equal to 0, right here. 0 for t, 0 for v, okay? So that's the simplest motion that you're going to see out there. One-dimensional motion with the object at rest. Okay, and I will I'm gonna copy and paste this graph there in my notes. But again, I risk having a note that end up being very large. Okay, here you go. Item 1, that's the special case. Okay, item 1. in the list, in the above list, X versus t. And then we can repeat that for the velocity. Here you go. Same case, but now I'm plotting the velocity versus t. Okay? And the velocity ends up being equal to 0. I'm going to do better. I'm going to do better than that. I'm going to put a little table here. Okay? And I'm going to put those two graphs side by side. Shrink them a little bit so it becomes clear. That's the same type of motion, but a different type of graph. Same type of motion, but a different type of graph. And by the way, you're familiar with graphs, right? I'm assuming that you folks are familiar with graphs, that you saw that in math and you learned that well. Everything that you have learned in math, we're going to be using here in physics. So here you go. Insert merge cells. Here you go. Two different types of graph. Same type of motion, Different graph, let's put it this way, different graphs for the same type of motion. Different graphs for the same type of motion. V equal to 0, V equal to 0. Item 1. Item 1 of the above list. Different graphs for the same type of motion. X versus t, V versus t. Even going to put it here, label it. X versus t. V versus t. Okay, the other type of motion, one-dimensional motion. One-dimensional motion is the object. And don't forget, this is instantaneous velocity, right? One-dimensional motion is the object moving. Is the object moving with constant velocity, and I can, right? That's what, and it looks like that. It looks like that, okay? Constant velocity greater than 0. When I even put constant velocity greater than 0. Now the type of the motion start to become a little bit more complicated, okay? And I use the school email for Wiley Plus, right? No, it can be your own email. It doesn't have to be the school email. I don't think that has to be the school email. Try that with your own email. Okay, Jeremiah? That was a question by Jeremiah. So here you go. Next. And then I'm gonna show you. Here you go. I'm gonna do the same thing. Greater than 0. Okay, and next, the velocity is still a graph similar to the previous one, but because it's at non-zero velocity, then the horizontal line is above the t-axis, right? Yeah. This this graph introduces a concept that I didn't mention yet, which is the acceleration, okay? So let's stick to those two first, okay? V, different graph for the same item 2 of the above list, different graph for the same type of motion, V greater than 0, okay? But then we can also have V less than 0, okay? Greater than 0. So we can go for the next one, one-dimensional motion with the object moving its constant velocity V less than 0. And how does it look like? Different graphs for the same type of motion, V less than 0. Same type of motion being constant velocity. Let's see. Different graphs for constant velocity, okay? For constant velocity, V equal to 0. Different graphs for constant velocity, V greater than 0. Different graph for constant, I still didn't, constant velocity, V less than 0. Let me erase that. Let's see if I can get that. Oh yeah, here you go. I do have it. Everything is here. Right? I have been updating those notes, for several years I have been doing these notes. I started with a blank PowerPoint, and now I have all those slides right in here. Copy. That's negative velocity, constant velocity less than 0. The nice thing about intellectual property is that it's cumulative. Okay? You can always keep on adding to it. And especially with computers. Nowadays, computers is even more easier to store it. In the past, when we didn't have computers, we had to keep our notes in paper, right? I'm from those times. Computers were not accessible to all of us. We didn't even have word processing software, and we have to write everything by hand. I remember even as far back as 1998, when I was teaching in Puerto Rico, I had to keep my notes in writing in a little notebook for my students. And those things would occupy a bunch of lots of space. So here you go. So I am introducing you now to this important type of motion, uniform motion. Okay. There are more. But we will concentrate on this type of motion. This type of motion that's called on the type of motion that's called uniform motion. Uniform motion or constant velocity motion. Constant velocity mode. Don't forget it's constant velocity, not constant speed, right? I'll copy and paste this guy right here. Right here. There are other types. There are other types of motion, but we will concentrate on the simplest one. Called uniform motion or constant velocity motion. Okay. Item 1, 2, and 3. Now that I introduced the concept of instantaneous velocity, we can talk about uniform motion. Okay? Uniform motion, just like I said before, is defined as the type of motion in which the velocity is constant. The instantaneous velocity is constant, or v equal to constant. Okay. Going from this definition, we will determine the so-called equations of motion. And what is this equation of motion? In which, or, position as a function of time and velocity as a function of time, okay? Though that's what the equations of motions are all about. It's a mathematical description of the position and the velocity. The position and the velocity, both of them as a function of time. That I have introduced, right? So in order to do that, we must start with the definition of average velocity. Remember that? So here you go. I'm gonna get that definition of average velocity that we got right in here. Average velocity, right in here. Okay? That's the definition of average velocity. I don't need that for now. Because the motion is uniform, okay? The average velocity will coincide with the instantaneous velocity. Do you agree with that? With the instantaneous velocity. By its very definition, right? Because the motion is uniform, the velocity is constant all the time, the average velocity will coincide with the instantaneous velocity. So let's write that. It's in boldface here. It's not supposed to be in boldface. Okay. Okay, so here you go. Average velocity is equal to v bar, which is another way of representing the average velocity, right? But, so I can also write that the average velocity coincides with the instantaneous velocity because of the type of motion that we are describing, delta x over delta t. This is a definition. What you see above is not the equation of motion. What you see above is not the equations of motion. Equations of motion that I mentioned. Instead, is one of our definitions, which one of our useful, not just that one of our definitions, but one of our useful definitions, which will be used to get the equations of motion. Okay? So how do we do that? Here you go. Now I don't need to keep on repeating the average anymore, but just instantaneous velocity is equal to delta x over delta t. Delta x is going to be spelled out as being final position minus initial position. Delta t is going to be spelled out as final instant of time, initial instant of time. But it happens that the initial instant of time can arbitrarily be defined as being 0 seconds. So I'm gonna put that 0 seconds right here. Okay? Most of the time we can do that in our equation of physics. X minus x naught over t. I didn't get the equation of motion yet, but I'm getting there. By definition, one of the equations of motion is the functional relation between the position and time. Okay? Do you see the position here in this formula? Okay, I'm gonna just copy and paste here. I'm gonna paste just one of the formulas so you don't get lost in that. In so many, do you see the position here? That's the position, right? This one here is the initial position. Okay, so what I want to do, I want to write this x here as a function of t. And that's not difficult to do that. Just by using algebra, we pass t to the other side. And now we have delta x. And I am going to, emphasize that we want to solve the equation for this parameter that you see right here. So you can get our equations of motion. And in order to do that, all I have to do is to pass the x naught to the other side. And we change the sign of x naught. And I'm going to rewrite with x on the left side of the equation. And that's our first equation of motion. Okay? Vt plus x naught. V is constant. X naught is also constant. Always the same. This equation is a linear equation in T. This equation is linear in T. Okay? And makes sense because when we plot it, we get exactly a straight line. Okay? The slope of this straight line is going to be the instantaneous velocity, delta rise over run. That's the simplest type of motion you're going to see out there. This is the simplest type of motion that you're going to see out there. You will see out there. In this equation, x naught is the initial position, and mathematically is referred as the intercept. Likewise, V is the instantaneous velocity, and mathematically is referred as the slope of the equation, slope of the above equation. Okay. Because V is a constant, because V is a constant, comma, it is not a function of time. Okay. So, in summary, the equations of motion for uniform motion for an object undergoing uniform motion is, okay, and I'm going to put the second equation of motion, and I'm going to emphasize that it is a constant. Okay. Okay, so now we have all those important definitions, right? We have the definition of position and velocity. And then there is another important definition in physics called the acceleration, and we represent it by the letter A. Acceleration is defined, its definition, it is defined as, you know, oh, even better, it's not just acceleration, the average acceleration. Okay. It is defined, remember, average velocity, something like that, right? So our average acceleration is going to be one step up, okay? But instead of delta x over delta t, right? We're going to change delta x by delta v, okay? So the progression is you have seen the progression, right? So the natural progression of the parameters is the following. First, we have position, then we have velocity, and then we have acceleration. That's the natural progression. If the average velocity is delta x over delta t, average acceleration is going to be the next step up, delta v over delta t. Okay? Having said that, we can now calculate the average acceleration for the case of uniform motion, right? That's easy, right? That's easy. So in this specific case, here you go, it's delta v over delta t. Delta v is going to be final velocity minus initial velocity. But I already told you that the velocity doesn't change, right? If the velocity doesn't change in uniform motion, it means that v must be equal to v naught, right? Or v naught must be equal to v. If v is equal to v naught or v naught is equal to v, the acceleration for this type of motion must be zero. The unit for the average acceleration and the acceleration in general is the meter per second square. Okay? Every time there's a change in the velocity, every time the velocity changes, we have an acceleration. For this specific case, we can even state for uniform motion, we always have the following. Average acceleration is always equal to instantaneous acceleration, right? Which will always be equal to 0. So let's go back here to our list of definitions. Definitions, right? Here you go. And now we can start filling up our definitions. Average velocity, instantaneous velocity. Now we have average acceleration. Okay? And after average acceleration, we have instantaneous velocity or instantaneous acceleration, which is defined in the same way that we defined the instantaneous velocity. Okay? And I'm going to copy what we had before. Here you go. If we have instantaneous velocity being the limit of delta x over delta t as delta t goes to 0, then for instantaneous acceleration, we're going to have the limit of delta v over delta t as delta v and delta t goes to 0, and it's also a finite number. And 55 can go a little bit more. And if we do a dimensional analysis, right, just like we did before as well, we can state that the dimension of average velocity as well, the dimension of average acceleration as well, the dimension of instantaneous acceleration, okay, is the unit of delta v over the unit of delta t, which is the meter per second squared. Okay. And then we can do some simple examples. Okay, here you go. Example 3 in the book. I'm going to display that to you. It's just straightforward applications of formulas. Okay, calculate the average acceleration for the case in which, the final velocity is 260 kilometers per hour and the initial velocity is 0, right? Let's take a look at this problem in the book. Announcements, course resources, right here. Launch. Chapter kinematics in 1 dimension. Is it the right one? Let's see, example 3. Acceleration. Example 3, right? Okay, here we have the case of an airplane, figure 2.4. This is a real life example, okay? We have this airplane that is initially at rest. Initial velocity is 0 at t equal to 0 seconds. And he's about to take off. So what do? You put power on their engines to accelerate your airplane, and the airplane must get to a velocity, a given velocity in which it can take off, okay? That's how airplanes fly. They manage to fly because they are flying fast enough to produce a force in the wings that provides lift. That's how airplanes work. And that's the wings of an airplane, how they work. Only up above a certain speed that you can achieve lift, that can start to fly. You take away the wings of the airplane, it's going to be very difficult for the airplane to fly, unless it has a proper fuselage contour to it, like the space shuttle. Okay, so we have this numerical example that's rather straightforward, okay? I define it that after 29 seconds, the airplane reaches a final speed of 260 kilometers per hour. Plus sign indicates the velocity points to the right. Determine the average acceleration of the airplane. Okay? So we can do that. It is a rather straightforward problem. In physics, you're going to see all sorts of problems, right? The ones that are easier, the easier problems are the ones that are straightforward application of formulas. And then you're going to see difficult problems. Difficult problems are those ones that are not a straightforward application of formulas. The difficult problems are problems in which you have you solve the problem by applying more than one formula. Okay, and this one applies this is straightforward definition here. So here we go. And how do we do? Average velocity, average acceleration is the final velocity, 260 kilometers per hour, minus the initial velocity divided by delta t, 29 seconds, right? And by the way, it's 260 kilometers per hour divided by 29. And by the way, we need to change our units to meter and second. See that? And it's rather straightforward if you know how to convert those units that are not in the SI main unit. 1 kilometer is 1,000 meters. 1 hour is 3,600 seconds. Okay? Those two zeros cancel out. 10 divided by 36, and when you do the math, you get this value for the average acceleration of 2.49 meters per second squared, okay? That's a straightforward example. A straightforward problem. Example 3 in the book. Okay, very important, acceleration and velocity can be either positive or negative. Okay? And now we can add the acceleration to our equations of motion. Okay, so you're ready. Now we can add the concept of acceleration to the list of of our equations of motion. Our equations of motion. Okay, so and that here you go. If x is a function of t, v and a can also be a function of t. F of t, g of t, h of t. Okay? We already saw that for v constant, the acceleration is going to be 0. From the very definition, right? From the very definition. And for uniform motion, we also saw that. For uniform motion, we have those equations of motion. X equal x naught plus vt, v equal to constant, and a equal to 0. Okay. And now we can move to our next type of motion. The next type of motion is the one that is referred as uniformly accelerated motion. In other words, a is equal to constant. Okay. And now let's go back to our list of different problems, right? Because okay, one-dimensional motion with object at rest. One-dimensional motion with object moving with constant velocity greater than 0. One-dimensional motion with object moving with constant velocity less than 0. And now one-dimensional motion with object moving with constant acceleration. Okay, the acceleration can be less or more than lesser or greater than 0. Okay, that's the next level of difficulty here. And what you find the equations of motion for uniformly for an object Now we can treat that as an example, right? Example. Here you go. Find the equation of motion of an object undergoing uniformly accelerated motion. Given x naught, v naught, what else? As a function of t. Given x naught, v naught, do I need anything else? I don't need anything else. Given x naught and v naught. Okay, so here you go. Solution. Uniform accelerated motion. Given x naught and v naught, here you go. Given x naught and v naught, comma, find the equation of motion as a function of t of an object undergoing uniform accelerated motion. Okay? Oh yeah, given, there's one more thing here that's missing, right? Given x naught, v naught, and a, right? That's the one that's missing here. The uniform accelerated motion. Okay, the way we do it is very similar to the way we did the other one. And I'm even going to copy the script of the previous one. Okay, and here you go. Here's the script. See that? We started with average velocity. And then we ended up with this equation. And I even gonna copy all this stuff. Okay. Solution. I call that the script, right? The only thing that's changed are the definitions. Okay, instead of average velocity, we are calculating the average acceleration. And because the type of motion is uniform accelerated motion, the average acceleration coincides with the instantaneous acceleration. And instead of delta x over delta t, it becomes delta v over delta t. Okay? So now we don't need that anymore. You know what? Let's leave it this way. Because the motion is uniform, the average acceleration coincides with the instantaneous acceleration. I'm doing step by step here, right? Here. Delta V over delta T. What's that? It's not the equation, it's not one of the equations of motion yet. It's not one of the equations of motion yet. Instead, this is all when acceleration is constant. That's right. That's right, Sean. Yeah. We're doing this special case of constant acceleration, which is a very important type of motion, okay? We do that here because there are practical applications of this type of motion in real life, yeah? And we're going to see that one of the practical applications. Instead, is one of our, what we see above is one of the equations of motion, is not one of the equations of motion, yeah? Instead, is one of our useful definitions, which will be used to get the equations of motion, okay? And now here you go. Instead of V, we replace by A, right? A is delta V over delta T. Delta V is V minus V naught. V minus V naught. Okay, over T minus T naught. T naught can be always taken to be equal to 0 seconds. And we get this equation here, okay, which I'm going to here right here in, oh, there's more, let's see. As we move x naught, v naught, yeah, okay, and a. Given x naught, v naught, and a, find the equations of motion, okay, we're there. So one of the equations of motion involves the parameter v, instantaneous velocity. Okay. And now I'll have to solve for v. Okay, and how am I gonna do it? I'm gonna replace my v here by a, right? Here is v, here is v naught. T naught is 0, so I pass my t to the other side. That's what I got right here in this line. And then, since I want to v as a function of t, all I have to do is to pass the v naught to the other side. And that's what I get here, v naught, replacing v with a, x with v, right? And now we finally get our first equation of motion. We derived one of our equations of motion. We're not done yet. We're not done yet because we do not have x as a function of t. Okay? We still do not have x as a function of t. At this point in time, we do know that a is a constant. Okay? And now we need to find x as a function of t. Notice that my velocity is linear in t. Okay? I'm gonna take this one out because it's, let's see, yeah, I don't need that anymore. And now we are going to find out x. How we can find x? Okay. There is a little trick to find x. To find the v is kind of straightforward. All you have to do is to apply the definition that you saw for acceleration. But now to get the x is a little bit more tricky, okay? Now we need to find the x equal to ft. In order to find that, we need to get an equation that involves x. Right? One of the equations that involves x is the one for average velocity. Do you remember that? Okay. So let's see if we can get anywhere using that, right? So here you go. That's the equation for the average velocity. Delta x over delta t, right? I am specifically mentioning average velocity and put this bar here at the top, okay? And it has to be average velocity. But remember, in the case of uniformly accelerated motion, the velocity changes linearly with time. Okay? So the average will no longer be V. Okay? Watch out for that. We cannot make V average equal to V because V is actually changing in this specific case. Okay? For this reason, we must come up with a second definition of average velocity. One that is independent of the above definition. All right? And there is just this right average velocity equation. That applies not just to average velocity, but applies to other things too. That will help us solve this problem. Okay? If this one here is average velocity, there is this other definition of average velocity that's given by the following. Final velocity plus initial velocity. Notice that I put a plus here, right? What else? Divided by 2. Do you recognize this definition of average? You get, the final value, you add to the initial value and divide by 2. Okay? And this definition of average also works very well for this type of motion that you see here, because the velocity is linear with time. Okay? And now we have two equations. I'm going to put them side by side now. Here you go. Like that. Two equations side by side. We want to find x, okay? We want to find x given v naught, x naught, and a as well. And t, right? And finally t. But where a would get into our equation? Remember that we just calculate the final velocity. The final velocity is this one right here, where a is, which is a function of a. Okay? And now, here you go. We can continue our derivation. I'm going to replace v with the equation with one of the equations of motion that we found initially, right? Okay, here you go. We see v naught plus v naught here. It becomes 2 v naught. Okay. And now what can we do? We can make this equation here equal to this other equation. Okay, 11:20. We're going to have our break very soon. And when we do that, we will be able to find our equation of motion for x. The equation of motion for x. That's what we get here. Okay. So I want to solve for x. And in order to do that, we have to pass the t to the other side. Right? And okay, I'm gonna put it here, just outside the division sign. But I'm going to do more than that. Before I solve for x, I'm going to distribute the t. Okay. Oh, not this one here. And then I'm going to simplify even further. I'm going to simplify that in terms of the formula that we use. Okay, here you go. First term of the numerator, right? First term of the numerator, at squared divided by 2. And now I can simplify this 2 with this 2 here. I didn't finish my derivation yet. I'm almost there. Okay. I'm gonna make it simpler so you can see the formula more easily. X minus X naught. And last step, this term here. $11.22 goes to the other side and change the sign. Okay, that's our other equation of motion. I'm gonna put that side by side with the other two, right? Okay, those are the equations of motion for uniformly accelerated motion. Okay, and it's 11:23. Let's see, maybe we have time to do one more thing here. There is one more, but I want to add that other one, but the other equation here, not this one, sorry. Is, where is that? What is that? What is that? The average. Oh yeah, this one here that I want to add. Because this one is not obvious, right? Average. Oh, like that. There is one more important equation. There is one more important equation that I want to derive. Because it's also useful. It's also very useful. Okay. One that involves only V naught, A, X, and X naught. But let's do that after the break, since it's already, yeah, 11:24. Let's take a break first. Break, 11:25 a.m. to 11:40. 11:40 a.m. Okay. Okay, so I see you in the next 15 minutes. I am back here with the book press problems. Yeah, what's the best way to press using these equations? Yeah, it's the book press problem. You can see, you can look in the internet, sure, you know, and but I like to tell my students, okay. Let me start sharing the the best way, the best way to practice those equations is to look at examples, right? Best way to practice those equations is first, these equations, right? Is one, solving the examples, right? That's the first step, solving the examples in the book. That's the first step, right? Try first, first try to solve these examples without looking at the solution. First try to do that. But don't burn yourself out, right? Don't try to solve it in every possible way without looking at the solution. Otherwise, you might end up frustrating yourself, right? So, but don't get yourself burned out. Try to solve, but don't get yourself burned out if if you can't solve it by yourself, right? Let's say, spend 10 minutes trying to solve it on your own. And if you cannot, if you can't figure it out, figure out the solution. Come on, look at how the book solved it. How the book solved it, right? And then move on to the end, move on, and move how the book solved it, and then repeat the solution yourself. Solution yourself on your own. Then repeat the solution in your own, right? In your own. Okay? And don't forget, the more problems you solve, let's say, the better you will get at it. You know? Practice, right? Practice, right? You do not become proficient just by solving 2, 3 problems, right? You don't become proficient by solving only 3 problems, right? 3 problems. You have to solve as many as you can. You have to solve as many as you can. But again, but again, do not overdo it. Or you can get yourself burned out, right? Do not overdo it, or you may get yourself burned out. That was a huge mistake that I made when I was a student, you know? I would become obsessed in solving those problems and I couldn't solve them and I would end up burning myself out. But there were other factors also involved, okay? When I was an undergraduate student. The other factor is that we didn't have air conditioning at my time. Remember, I was in Brazil, right, doing my undergraduate work. And back in the 80s, air conditioning was was a luxury for us. Air conditioning was a luxury for us. Nowadays, not only it was expensive to buy air conditioning, and it was also expensive to maintain the air conditioning because the air conditioning spent too much energy, and the electricity bill would go all the way up there. My mom would scream at me, and so look at those other things too. While you are solving your problem, while you are solving problems, okay. Also, look at the comfort aspect, right? Do not underestimate your comfort aspect. Comfort aspect. By comfort, I mean not just AC, not just the temperature, but also the relative humidity, right? Relative humidity is very important. Air conditioning is, if the relative humidity is not right, you may not feel comfortable, even though the temperature might be just right. The relative humidity the chair you use, very important, the chair you use, buy a very good chair, buy a very good and comfortable chair and table, right? So those are hints that I give you because, when I was growing up, when I was going through undergraduate school or studying to go into undergraduate school, I didn't have any of those comforts that I have today. I didn't have air conditioning. I have a lousy table. I had a lousy chair, and then later on in the day, after studying 8 hours the whole day, I was complaining about muscle pain. I was complaining about back pain. Oh man, that thing would consume me. It was terrible. Okay, so look for those things. Okay, and don't save on your comfort. It's very important that you're very comfortable solving your problems and understanding the problems. I don't recommend you sitting down in the floor to solve problems because you're not going to get a good posture. You have to have a good chair. You have to get a good table, and definitely air conditioning. Definitely air conditioning with a good relative humidity in your room. You know. And going back to the problems, right? There are problems that are very easy to solve. Okay, don't forget, going back to the problems, right? Going back to the problems. You know, there are all sorts, there are all sorts of problems out there, of physics problems out there. Some of them are straightforward to solve. Forward solve. Okay? These problems, they just require um, straightforward application of the formulas, of a straightforward applications of a very important single formula. Okay, single formula. Okay, a very straightforward, a very simple problem in physics, for instance. I'm going to give you an example of a very simple problem in physics. A very simple physics problem is one in which given is the following. Here you go. Given x naught, and delta t, right? Find the average. Okay? That's an easy problem, right? Because it's a straightforward application of the following formula. It's just, I don't know, did I put delta? Okay, this one is supposed to be delta V here. Okay? So it's a straightforward application of this formula here. Right? There is no secret, right, in how to solve this type of problem. But it's not going to be every problem that's going to be easy, right? There will be problems that are going to require more from you, and see that given to solve this problem, all you need is a single equation, right? It's a single equation that is easy to memorize, right? The definition of average velocity. Another easy problem is this one here. Given v naught and delta t, find the average acceleration, right? This is an easy, straightforward problem too, right? All you have to do is plug in the numbers in there, punch your calculator, and get the result. Okay, and this equation also is easy to memorize, right? More challenging problems involve the application of two or more equations. Those are the difficult problems. You know, difficult problems are the ones that involve two or more equations to solve it, or more equations to solve it. So those are the challenging ones. So there are those problems that are straightforward to solve because all you need is a single equation. And then there are the difficult problems which require more than one equation to solve. Okay? And I'm going to provide you along the way, I'm going to provide one example that involves more than one equation. Okay? But let me finish what I start to do. But I think, those are very good ways of help you solve problems in physics, okay? Well, what I want to do now, we have 7 more minutes to go. Let us finish what we started. And what I want to do, I want to derive another equation, and I'm gonna put that right in here, okay? Insert it right in here, so it doesn't break the continuity of my thought process. Let us finish what we started, okay? So there's one more important equation that we must derive because it's also very useful. One that involves the v naught, ax, and x naught, okay? In this useful equation, we must eliminate the t parameter. Okay? So we have only, so we can finally get an equation that involves a function, let's say, of v naught, x, x naught, and a. Okay? That's how we would write it in a mathematical fashion. This notation, by the way, is kind of universal, okay? Whether it's in Brazil or the US and maybe even in China. So how do we do? We start here with our equations of motion, right? Here you go. And we must eliminate t. Notice that there is no t here. That's why I can tell you that I must eliminate t. In order to eliminate t, I have to write t in terms of the other parameters, okay? We must eliminate t. And to do so, we must write t in terms of the other parameters using the available equations. Okay? So here you go. We have 1, 2, 3, 4 equations. Okay? Note that we have 4 equations. However, out of these 4 equations, only 2 involve the parameter t, right? So out of the bat, you can eliminate those 2 equations for your derivation, okay? So only 2. All of those 4 equations, you're going to need only 2 to write your new equation, okay? And to eliminate t, okay, here you go. It's easier to eliminate t using this equation here, because this one here is a quadratic equation, right? You don't want to, if you can avoid dealing with two different solutions that involve square roots, you're better off doing that, right? So we are going to use the equation, the linear equation, the equation that's linear. Okay, first step. 2 more minutes to go. Here you go. Second step. Second step. Okay. Oh, no. I want to put A here. T equal to that. Remember that I told you the more difficult problems are problems that involve more than one equation? This is the type of difficult problem that involves two equations. Actually involve 4 equations, right? And it requires some effort to find out if you're going to use the 4 equations or not. Okay? And finally, we end up discovering that out of the 4 equations, we need only 2. And then we go ahead and use those 2 equations to achieve the solution that we're looking for. Now that I didn't eliminate t yet. I wrote t in terms of the other parameters, right? Now that I wrote t in terms of the other parameters, we are going to eliminate t from the other equation, this equation right here. Okay, here you go. Emphasize the t, both faces, and substitute it right here. Right? Here you go. I'm gonna do the same with this other one here. Well, 1 minute to go. Oops, I hate this mouse. This mouse gives me such a big trouble. Okay, here you go. Now I eliminate the t in this equation. And now the next step is just algebraic. Okay, it's just all you have to do now is to develop your equation algebraically. Okay, and what I'm going to do, I'm going to put a parenthesis here. No, and I'm going to square here. All I'm doing here, I'm distributing the factor, the square, distributing the square. And here I will have to expand right? Or distribute. I don't need the parentheses anymore because yep. Next step. No, it's just algebraic procedure. Here I'm going to expand the square of the first, square of the second. When I do the square of the second, I change the, oh, okay, yeah, like that. And then I do the cross product, right? It's minus, yeah, it is minus, and we no longer need the square on the outside, right? And this A can cancel out with this other A. Here you go. I'm gonna copy and paste in the next step. I'm going to simplify this A with this A. I'm gonna do more. I'm gonna pass the number 2 here downstairs, so it's not separated by the other. And then what I'm gonna do? We're going to combine those 2 fractions, okay? That's what I'm gonna do. Under the common denominator. In order to do that, I'm going to put I have to write down a common denominator here in the second fraction and combine them. I'm gonna combine in the next line. Okay, this term I is going to come right in here. What time is that? Oh man, 12:02 already. Okay, we're running out of time here. Okay. I'm not going to do the final steps, okay, but you can see that this VV naught here cancel out with this VV naught. This plus V naught square cancels out with this 2V naught square, right? And we have a V square here. And I'm just giving you the final answer because we run out of time already. And what's the final answer? The final answer is like that. Is V square equal to V naught square, okay, plus 2A delta x. Okay? That's the other equation that you have to keep in mind whenever you solve your problems. And I'm going to put them all together right in here. Okay? If you memorize them, it's better, it's best, because it helps you solve the problems more quickly. But those are the equations that you gotta know for this type of motion, which is uniformly accelerated, okay? Any questions? I have office hours now. If you want to hang around, let me know. And if not, I'll see you on Wednesday, okay? See you on Wednesday.
Bye, Professor.
See you, bye-bye. Let's see. Wednesday.
Will you be posting this lecture in Canvas today?
Yeah. Posting you mean the recording?
Yes.
Yes, I'll try to post it today.
Okay, thank you.
But,
Have a good
remember,
one.
it takes some time for not just for my computer to prepare the recording, right? But also for YouTube, right? To prepare the recording. So, I'll do my best to get it as soon as possible.
Okay, thank you. Have a good one.
You too. Bye bye. Let's see. Thank
Hi,
you,
Professor. I have a
everybody.
question.
You. Recording.